universe is vast. It is large, very, very large. Because of this, NASA has no current plans to transport humanity to any of the thousands of known planets outside of our solar system with a conventional spacecraft. The closest star and planetary system to Earth is Alpha Centauri, which is 4.37 light-years away. However, using current technology, it would take a person about 6,000 years to travel there. We need to develop a new method of interstellar space travel in order to traverse the vast distances between Alpha Centauri, other exoplanets, and our own solar system. Could we reasonably expect to go to any of the nearby stars? How does NASA plan on getting to these faraway planets? Let's find out. NASA has some big ambitions for human crewed space missions in the future. And when they say enormous, they often mean vast or galactic spanning at least. See, the unfathomably large size of space is the one major problem with manned space travel. Since the numbers used to represent distances within the cosmos are so enormous, astronomers had to develop a new unit of measurement, the light year. Even the closest stars will take hundreds of years for humanity's fastest spacecraft to approach. Additionally, humankind will require a propulsion technology that is a great deal more powerful than traditional rockets if it truly wishes to travel to the furthest stars. With one, people would be able to travel to star systems that are light years away from Earth. However, an interstellar mission to look for life beyond our solar system has been revealed by NASA. In 2069, the 100th year of the first moon landing, the US Space Agency intends to launch a robotic spacecraft to the nearby star system Alpha Centauri. 3 stars make up the constellation Alpha Centauri, which is only 24.9 trillion miles away from Earth. Centauri A, Centauri B, and Proxima Centauri. Since an Earth-like planet was found orbiting Proxima Centauri in the past year, it has attracted a lot of scientific and public curiosity. The planet, known as Proxima b, is situated in the habitable zone of Proxima Centauri, where the climate is suitable for liquid surface water to exist. There are almost certainly little Earth-like planets in Alpha Centauri that are capable of supporting ET life. However, it is frequently bombarded by intense ultraviolet and X-ray radiation from the star, so any life that evolved there would need to be radiation resistant. According to astronomers, the Alpha Centauri star system very probably contains more small Earth-like planets that could support extraterrestrial life. However, in order to get to Alpha Centauri, a spaceship must be able to move at a minimum of 10% the speed of light, or roughly 30 million meters per second. Even if this were possible, it would still take 44 years to go there, putting the arrival at Alpha Centauri in the year 2113. According to reports, NASA is looking into various options, such as deploying tiny laser-powered probes that could theoretically travel at a quarter of the speed of light. Star travel is not possible with standard rockets. They move far too slowly. However, researchers from Penn Engineering and the Breakthrough Starshot Initiative announced in February 2022 that they are developing a new means of reaching the nearest star system. Their fresh idea makes use of an improved solar sail. If it is successful, in as short as 20 years, it might arrive at Alpha Centauri. The idea originated from a statement by Russian high-tech billionaire Yuri Milner in April 2016. He started a brand new ambitious project called Breakthrough Starshot with the goal of investing $100 million in proof-of-concept research for a completely new space travel technology. In order to get to the Alpha Centauri system and, most likely, its recently found planets Proxima b and Proxima c, it was designed to travel at a speed of 20% of the speed of light. But is it even feasible? That question has been the focus of research. A solar sail spacecraft ought to function for star travel in principle. In actuality, though, the sail must endure the arduous trip to Alpha Centauri. The new studies emphasize a solar sail that is more robust and long-lasting, according to Igor Bogatin of Penn Engineering. Within our lifetimes, relativistic speed, or close to the speed of light, will be needed to travel to another star. Although the concept of a light sail has been around for some time, we are only now learning how to ensure that those designs endure the journey. The upcoming probe is incredibly little. It resembles a microchip in size. The sail is extraordinarily thin, about 10 feet or 3 meters wide, and 1,000 times thinner than a sheet of paper. It is made up of molybdenum disulfide and aluminium oxide sheets that are incredibly thin. These scientists claim that this tiny probe from Earth might reach a speed of up to 1/5 of the speed of light by using lasers. That travel speed will take 20 years to reach Alpha Centauri. Earlier iterations of solar sails were solely powered by sunlight. However, Starshot's new design would use ground-based lasers to assist in accelerating the sail. Millions of times more light would be produced than if only sunlight were used. The sail must, however, be able to endure the risk of tearing or melting in order to do this. The first paper's topic, having the sail billow out like a parachute rather than staying flat, is one solution. It would be around the same depth as width. The pull of hyperacceleration, which is hundreds of times stronger than the gravity on Earth, could not break such a sail. The underlying assumption is that a highly tight sail, whether in space or on a sailboat, is much more likely to rupture. Although the idea is rather simple, we needed to perform some extremely difficult mathematical calculations to demonstrate how these materials would react at this scale. Similar to how air inflates a beach ball, laser photons will fill the sail. We also know that lightweight pressurized containers should be spherical or cylindrical to prevent rips and splits. Consider fuel tanks on rockets or propane tanks. The second study examines methods for releasing laser heat. The solution, according to the researchers, is nanoscale patterning, nanolithography. The act of imprinting, writing, or etching patterns at a tiny level in order to produce exceedingly small structures is known as nanolithography, which is a subfield of nanotechnology. The sails will heat up to very high temperatures if they even have a small portion of the incident laser light. We need to make the most of their ability to reflect heat out, which is the only form of heat transfer possible in space, to ensure that they don't simply disintegrate. However, therefore, may the sail's thermal radiation be maximized. The material of the sail was introduced with holes that were evenly spaced in earlier iterations, which used a photonic crystal design. The latest research advises tying sail fabric swatches into a grid as an extra kind of protection. This increases the sail's ability to resist tearing and melting twofold. The hole's spacing and the swatch's spacing are matched to the wavelengths of light and thermal emission, respectively. The sail can endure a stronger initial push from the lasers by doing this. As a result, the lasers don't need to be focused on the solar sail's target for as long. All of this sounds fantastic, but why can't we just use conventional rockets? Take into account the space shuttles, which entered Earth's orbit from just a few hundred kilometers above the surface of the planet. In comparison to the corresponding 6-mile or 10-kilometer distance to Alpha Centauri on the same scale, this distance is roughly the breadth of a hair if Earth were the size of a sand grain. Although we have created starships, the space shuttles weren't starships. 5 spacecraft from Earth are now leaving the solar system and traveling through interstellar space. The New Horizons spacecraft, the 2 Pioneer spacecraft, and the 2 Voyager spacecraft are included. Compared to the speed required to move among the stars, everyone is moving incredibly slowly. So let's think about the 2 1977-launched Voyager spacecraft, Voyager 1 and Voyager 2. Although neither Voyager is pointed at Alpha Centauri, if one were, it would take tens of thousands of years for it to arrive there if it kept moving at its current rate. The Voyagers will eventually pass other stars. Voyager 1 will come within 1.6 light-years, that's 9.3 trillion miles, of AC 793888, a star in the Camelopardalis constellation, in roughly 40,000 years. Voyager 2 will pass 4.3 light-years away from Sirius, the brightest star in the sky, in about 296,000 years, 4.3 light-years. That's how far Alpha Centauri is from Earth. How about the New Horizons probe, the first probe ever to travel to Pluto and its satellites? The speed of New Horizons is 36,373 miles per hour. That's 58,536 kilometers per hour. It was launched from Earth in mid-January 2006, and by mid-July 2015, it had arrived at Pluto, 9.5 years later. It would take around 78,000 years for New Horizons to reach the Alpha Centauri system if it were pointed in that direction, which it is not. As a result, traditional rockets are ineffective because they are simply too sluggish. Suppose we had a warp drive. What if we could move at the speed of light? The idea is the foundation of countless science fiction literature and films, which poses problems for physicists' understanding of how space and time truly function. Still, a few years ago, Harold "Sonny" White, who oversees NASA's Advanced Propulsion Team at the Johnson Space Center, asserted to have made a finding that made the Alcubierre warp drive, a theory that would enable travel faster than the speed of light, possible. Is the NASA warp drive even real? And from where did it originate? Indeed it is. You would think that the theoretical performance of it originated from the overzealous imagination of a Hollywood writer, because the science behind it is so astounding. This notion is based on suggestions made in 1994 by Mexican physicist Miguel Alcubierre. He proposed that the space-time distortion might be used to enable faster-than-light travel. In order to better explore these theories, White has been working. They are pretty cool, but quite speculative. The great Albert Einstein and his theory of general relativity serve as the foundation for the tale of the Alcubierre drive. According to Einstein's equations, the presence of energy and matter causes space-time to bend. This then clarifies how the two objects travel across space. Deep space travel is subject to two restrictions imposed by general relativity. According to the first, if a spacecraft can't travel faster than the speed of light, which is approximately 300,000 kilometers per second, it won't be able to reach the universe's furthest regions in an acceptable amount of time, let alone the Milky Way galaxy. Nothing is faster than the speed of light, which is why Einstein referred to it as the cosmic speed limit. The second reason is that as a spaceship gets closer to the speed of light, its clock will slow down in relation to Earth time. Simply put, a spacecraft traveling at the speed of light would experience time much slower than a person on Earth. This phenomenon is known as time dilation. While hundreds or perhaps thousands of years would have already passed back home, the human crew aboard would have aged more slowly, thereby turning them into time travelers into the future. These are the primary guiding concepts of the NASA warp drive, but how do they work in technology? The use of the two general relativity ideas described is the most straightforward explanation for the Alcubierre drive. The NASA warp drive will use a huge quantity of energy to warp or contort and twist space-time behind the spaceship, which will result in the creation of a space-time bubble. The ship will potentially travel a shorter distance thanks to this bubble, which will be formed around it and curl behind it. As a result, it might enable travel at or even faster than the speed of light. The only issue is that it would be difficult to manufacture the quantity of energy needed for the NASA warp drive with current technology. Simply put, building the spaceship propelling bubble would require more energy than the entire universe possesses. However, traveling at the speed of light has some intriguing and potentially dangerous implications. There are so many potential problems. On to the workaround now. According to scientist Eric Lentz, the creation of a distinct kind of space-time bubble can be the solution to the issue of using excessive amounts of energy. He insisted that NASA should try to develop a bubble shaped like solitons. Solitons function similarly to ripples on a still lake in that they keep their whipping motion while moving at a steady speed. Lentz contends that this kind of space-time bubble would simply require standard methods of energy production. It's clear that NASA is still ironing out the wrinkles in their warp engine, but it might only be a matter of time until human crews can travel to or at least nearby star systems like Proxima Centauri. According to the research, other methods being considered involved using nuclear processes or collisions between matter and antimatter. How about the plans for the solar sail's future? The scientists will keep putting their novel solar sail concept through testing. According to Deep Jeriwala from Penn Engineering, a few years ago it was thought far-fetched even to discuss or do theoretical research on this type of concept. Now, in addition to having a design, we also have one that is based on actual materials that are accessible in our labs. Our future goals are to make such structures on a modest scale and test them with powerful lasers. The bottom line is that star travel is extremely far because of the enormous distances between stars. But in the near future, a revolutionary solar sail might be able to reach Alpha Centauri. We can only use our telescopes to gaze at the furthest stars till then. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.